Hello everyone. I hope everyone are doing good. Fine. In this session, I'll be giving a demonstration on module 3, image enhancement in the spatial domain. Yeah. So in the enhancement of an image, there are two types. One is enhancing with the spatial domain, and another one is enhancing the image with the frequency domain. So module 3 is all about image enhancement in the spatial domain. Yeah. So I'll be referring digital image processing written by Rafael C. Gonzalez and machine vision, automated visual inspection and robot vision by David Vernon. Okay, these two textbooks I'll be referring to give the demonstration in this session. So module 3, as I told, it is all about image enhancement in the spatial domain. The objective of enhancement is to get the processed image as the pure one, wherein the original image will be of raw, which consists of so many noises and as well as blurring. So in order to overcome from those hurdles, we'll be enhancing the image. So enhancement methods are of two types. One is a spatial domain, another one is frequency domain. So in this session, in this module, I'll be giving the demo on the spatial domain. Okay, in the upcoming module, that is next module 4, we'll be seeing the frequency domain. Fine. So module 3 consists of the following contents: the background of image enhancement in the spatial domain, and some basic gray level transformation, histogram processing, and then enhancement using arithmetic bar logic operations, then basics of spatial filtering, and then enhancement using arithmetic bar logic operations, sharpening spatial filters, combining spatial enhancement methods. So background, the first one, the background, spatial domain methods operate directly on image pixels. Spatial domain methods operate directly on image pixels. So if you see g of x comma y, this one, g of x comma y, and t of f of x comma y, here f of x comma y is the original image and t is the operator, and g of x comma y is the processed image. Okay. So f of x comma y is the original image, t of f of x comma y, when you apply some operations using t, that is transformation will going to happen, and g of x comma y is a transformed image. So t operates only for one pixel at a time. So here r is a single pixel. Okay, transformation of single pixel is a transformed pixel, that is S is a transformed pixel. So the applications of transformation is mapping, contrast stretching, thresholding, and the binary image. Fine. I hope everyone are fine with this one. Now background continues here. So if you see, there are two graphical representations and three images in this one. So let me talk about the first two images, this one and this one. So this is the first image, is the gray level image, that is gray image. Here you can see different types of pixels, that is three types of pixels. One is black pixel, another one is white pixel, another one is gray pixels. Okay, so when you slightly transform that one, if you enhance the image, when you enhance this one, you can see still some gray color images here. Okay, so what this graphical representation tells is the transformation between 0 to 1, that is converting grayscale image to the monochrome image or black and white image, we're going to call that. Okay, so when you convert a gray image to the black and white image, so in the black and white image only two pixels will be there, two types of pixels will be there, either black or white. You're going to call it as 0 to 1. But in gray, the pixels will be ranging from 0 to 1. Okay, so from the darker side to the brighter side, it is happening in the gray image, this one or this one, both the images. Okay, so from darker side to brighter side, it is increasing. Okay, so this range, this transformation is called as T of R. R is a single pixel, T is a transformation is happening there. Okay, but how the transformation T of R will going to happen in black and white image, that is monochrome image, it will going to directly convert like this. Okay, here it is happening linear wise, here exponential wise it is happening linear, and here exponential, sudden changes in this one. Okay, so I repeat once again, in the grayscale images, gray level images, the transformation is happening linearly here, slowly it is increasing. So this portion, whatever you people are seeing, okay, it is slowly converting from 0 to 1. But here in this image, what is happening here is sudden changes is happening. A straight line you can see here, 0, either 0 or 1. This side is called as darker side, this side is called as brighter side. Okay, now the background of continuous. T operates with the neighboring pixels also. Okay, T operate on the neighboring pixels also. How it will going to happen? Let us consider a matrix of 3 cross 3 size. Okay, so this is the matrix. This matrix is also called as the mask. You can call it with different names called as filter, kernel, template, window, whatever. Okay, so mask, generally everyone will be calling it as mask. Okay, this mask, when you apply on the image, let me consider this is some cross 5 matrix. Okay, when you apply this one, the mask will going to put it on the image like this. Okay, so this mask will going to change the values, multiplying with some values like say for example 1 by 9 or 1 by 16. Okay, so this 1 by 9 is a high pass filter and the 1 by 16 is a low pass filter. Okay, so these values will going to be multiplied with these pixels, each pixels, that in the coming slides we're going to see. Yeah, this is the mask, this is the mask, the value of this mask is here. Okay, so 3 cross 3 is there, 1 2 3 4 5 6 7 8 9, so totally 9 pixels are there here. 1 2 3 4 5 6 7 8 9 pixels are there. Okay, so m00 will be multiplied with f of x minus 1 and y minus 1. Here I'll be taking x and y like this. Okay, so x minus 1 and y minus 1, the previous pixel of this one is x minus 1, the previous pixel of y is y minus 1, the next pixel is x plus 1, here y plus 1. Fine, so there are 3 pixels you are seeing here. Here also 3 pixels with x coordinates. You have got 3 types of pixels. Y coordinates, 3 types of pixels. In the x coordinate, if you see, x previous pixel, neighboring pixel, previous neighboring pixels will be x minus 1. The next pixel will be x plus 1. So x minus 1, x and x plus 1. Y minus 1, y, y plus 1. So you are going to multiply this m00 with first x minus 1 and y minus 1. Okay, m00 into x minus 1 comma y minus 1 plus m01 into x minus 1 comma y, x minus 1 comma y, second pixel, and this first pixel with the second coordinate of the y pixel. Okay, next m02 is multiplied with x minus 1 y plus 1, x minus 1 y plus 1. So if you see here how it is combining x minus 1, y minus 1, yeah, then x minus 1, y, x minus 1, y plus 1. You are multiplying that one with the m00, m01, and m02. Okay, so let me take m10. You are coming to the next one. So this one is over. Y minus 1, y1, your combination is over. X minus 1 with y minus 1 combination is over. X minus 1 and y combination is over. X minus 1 and y plus 1 combination is over. Now let me consider the x. X with y minus 1, first combination, into m10. Then x with y, m11. Then x with y plus 1, m12 into m12. So this one you're going to call it as the second coordinate multiplication, that is f of x comma y minus 1 into m10, f of x comma y into m11, f of x comma y plus 1 into m12. You can see it here. Okay, so the last one, x plus 1, I'm going to see x plus 1 and y minus 1 combination, x plus 1 and y minus 1 into m20, x plus 1 into y, x plus 1 comma y into m21, x plus 1 comma y plus 1 into m22. So how actually it is working here is combination of summation of all these things is t of f of x comma y is equal to f of x minus 1 comma y minus 1 into m00, f of x minus 1 comma y into m01, plus f of x minus 1 comma y plus 1 into m02, so on up to f of x plus 1 comma y plus 1 into m22. So you already know this equation, t of f of x comma y, what it will going to give the solution. This is g of x comma y. So T is a transformation as operator which is going to work on single pixel and as well as the neighboring pixel. F of x comma y is a original image. G of x comma y is a transformed image. I think now you have clearly understood whatever I have explained till now. Okay, so the next point, some basic grade level transformations. Okay, so this is the identity. This is the identity where your image falls. Okay, so the negative portion will going to fall exactly opposite to that one. Okay, so the transformation, how actually it happens is, in the first place which is nth root, and the second place nth power. So let me consider the value of pixel is 4. Okay, nth root can be written as like this, that is n is 4 here, so square root of 4 is 2. Nth power 4 can be written as 2 square. Yeah, so the value of pixel can be transformed to 4 either the way, through nth root or nth power as shown here. Yeah, so another one is log and as well as inverse log. Logarithmic transformation, log 10 is going to become 1. Okay, inverse of the same thing is going to become 10. Some examples we shall see. So this is the negative transformation, image negative. This image is the grayscale image. The right side image of this one is original image, is the transformed image, it is negative. The negative of this one is the black pixels will going to become white color, and this portion white color will going to become black color. Okay, so this portion is become white here, this portion has become black, the negativity of this one. So original digital image this is, and this is the negative transformed image. Okay, so let us see one more example, that is a gray level transformation to the negative portion. Okay, if you see here also, this is the original image, this is the original image, and this is the processed image, that is negative image of this one. So can you able to see the difference in both the images? Yeah, if you see this portion, this is black color here in the original image. When I transform that one to the negative image, here you can see white color. The chest portion of the product is here white color, here black color, here also here opposite color. Yeah, now log transformation, that day in the class we have implemented all these things in the MATLAB and we have seen that. So when we have implemented, we also got the same type of results. This is the original image, this is the processed image. This one is going to enhance the brightness of the image. Here this is darker image and this is brighter image. This is one more type of ray level transformation. Okay, the first one what we have seen is image negative, that is one of the some basic ray level transformation. Another one what we are seeing is log transformation, that is original image to the processed image. If you see, the darker image has become brighter image. Now here contrast stretching, we're going to call one more type. Here is contrast stretching using piecewise linear transformation functions. Okay, so linear is increasing linearly. Okay, this is the low contrast image, and this is high contrast image. So when we apply the graphical representation for all three images, so the transformation is happening here. First image will going to fall on the darker side, because here to here this is increased little bit, and here to here it is high level contrast image. So piecewise linear transformation, when we apply on the second type of images, this is the difference. These two images, when you compare, which one is looking good? If you said the second image, you're right. So the first image is a little bit low contrast image, and this is high contrast image, wherein the information in the second image is too high. Okay, histogram processing. So when you apply the histogram on an image, you're going to see four types basically. So I am hist of image, input image. I am hist is the keyword you will be using in the MATLAB to generate the histogram. Okay, so here dark image is there, low contrast image is there, bright image is there, high contrast image is there. Okay, four images are there. What are those? Dark image, low contrast image, bright image, and high contrast image. When you apply the histogram on the dark image, all the bars in the graph will going to fall on the left portion. Okay, if you apply histogram on the low contrast image like this, all the bars will going to fall in the middle of the graph. Bright image, if you apply the histogram, all the bars will going to fall on the right portion. This is the high contrast image. Neither it is dark or not too bright, or it is low contrast also, it is high contrast one. So all the bars are equally distributed, isn't it? Yeah, so dark image, all the bars are fallen on the left portion, and low contrast image, all the bars are fallen in between the dark and bright, that is in middle of the graph. Right image, right portion. High contrast image, it is equally distributed. Okay, histogram processing, histogram equalization. This is so transform function S is equal to T of R. We already know what is T of R here. Okay, so S is the transformed pixel, R is the original pixel, T is transformation, where R should fall in between 0 and 1. That is dark, that is black pixel, and the white pixel. R is falling in between 0 and 1. The conditions for this one is T of R is a single valued and monotonically increasing, like this. Linearly it is increased monotonically, and not only this one, if this condition holds good, it also should holds good for this one. That is R, when it is holds good between, it is falling in between 0 and 1. T of R also should fall in between 0 and 1 itself only. The inverse of S is equal to T of R is R is equal to T inverse of S. So the condition should be 0 is less than or equal to S less than or equal to 1. Okay, so this is the direct equation of the transformation function. S is equal to T of R, and the inverse of that one is R is equal to T inverse of S. So histogram equalization is continuing. That is a cumulative density function is given by S is equal to T of R is equal to integration from 0 to R PR of W into TW, where W is the weight of each pixel. Then when you replace the values with respect to this, you're going to get it as, when you differentiate the transformed pixel ds by dr, you're differentiating the transformed pixel with respect to the original pixel can be written as d of t of r by dr. So what is t of r? Here we have already got from equation 3.3.4. We're going to replace with t of r. We're going to get d by dr of integration of 0 to 1 PR of W into dW. So you can directly write this equation as PR of R. Okay. So once again, whatever we have seen here, this one, whatever we have seen, this one can be summarized like this. The darker image using histogram transformation, we can make it as high contrast image. The first one is showing that one. The dark image is made to the high contrast image. The pixels are equally distributed. Okay, the bright image is been made to high contrast image and the pixels are equally distributed. The low contrast image is made to high contrast image and is equally distributed. Okay, so high contrast image to the high contrast image, again it is equally distributed. Okay, so this shows that the darker image or the brighter image or the low contrast image can convert into the high contrast image, and obviously all the pixels will be equally distributed. Okay, this is one more example when we are implemented in the MATLAB. This is the original image and this is the transformed image. This is the transformed image. So this is, low contrast image and this is high contrast image. So if you see the low contrast image, the bars in the graphs are following in between darker side and the brighter side. Here the bars are equally distributed in between darker side and brighter side. Okay, this is the example of MATLAB implementation. The next portion, enhancement using arithmetic and logic operations performed on a pixel by pixel basis between two or more images. Okay, so you'll be using the logic operations. We are all know that there are three types of logic operations: and, or, not, and arithmetic operations, subtraction and averaging. So shall we see this example, enhancement using arithmetic or logic operators? So this is the original image. So this is the original image and this is also the original image. So here you can see, and image mask. This is and image mask. And the third is result of and operation on images. This is the result. Opposite way how we can work. This is the original image. This is the or mask. This is and mask. This is the result of and operation. This is the result of or operation. Fine. Basics of spatial filtering. We're going to call that mask. This mask as a filter, kernel, template, window. This one we have already seen here. Yeah, this one. How you're going to elongate the mask. Okay, so here also is written in different template. Okay, different template. You can write g of x comma y, that is transformed image has summation of a to s is equal to minus a and b s is equal to minus b w of s comma t f of x plus s comma y plus t. Okay, fine. Smoothing spatial filter. The next point is smoothing spatial filter. Okay, so there are two types of spatial filters. One is smoothing and another one is sharpening. Okay, so smoothing spatial filter, the exact opposite of this one is sharpening spatial filter. In the smoothing spatial filter, what we're going to do is, if the original image is there, we're going to apply some transformation using the mask. This is original image. We're going to apply the transformation, that is t operator, and you're going to get smoothened image. This is smoothened image. Okay, so the exact opposite, opposite of smoothing filter is the smoothened image. You're going to take, you're going to apply the transformation, and you're going to get the original image. Okay, so here original image, this will be the transformed image. Here original image will be transformed image like this. So smoothing filters applications are blurring and noise reduction. Okay, smoothing spatial filter, there are two types of filters, 1 by 9 and 1 by 16. So averaging filter is 1 by 9 and low pass filter is 1 by 16. Okay, so averaging, when you, how we're going to work is, if the pixel if the pixel here 1 is there, no, you're going to multiply by 1 by 9, and in this one also you're going to multiply by 1 by 16. Okay, these values, converted values, will go into smooth the images properly. So these are the example of templates. You may ask that, sir, is this temple is the actual template and we have to use the same type? No, you can change it however you want based on your um, image. Based on the situation, you can change your template as you want. Okay, this is just an example. So smoothing spatial filter example has been given. So first image is been transformed, in it 4 different layers. The last result is showing the smoothened image of this one. Okay, so smoothing spatial filter helps especially in the satellites. So when they take the images and send to the control room, those images will be having so many noises in that one. In order to remove all those noises, you'll be using the smoothing spatial filters. Okay, particularly there are 3 phases in digital image processing. That is, first one is pre-processing, the second one is feature extraction, the third one is identification and verification or classification or recognition. Okay, if you want to get a promising result in the final stage, that is identification or verification, you need to extract the features properly. The more number of features you extract, the more promising result you're going to get. But in order to extract the features properly, you need to do the pre-processing properly. Okay, so this is one such example. This is the image from the Hubble Space Telescope. Okay, so it is processed by 15 plus 15 averaging mask. Result of thresholding is this. Okay, original image courtesy by NASA. Smoothing spatial filters, that is order statistics filters. In the class we have implemented all 3 of these things: median filter, max filter and min filter. Okay, so there are 3 types of filters in this. So median filter, we're going to take the median of the image and we're going to remove the noises in the image. Say for example, if you have taken an image, okay, so in this image if there are noise, let me consider the noise example, that is salt and pepper. There is one noise available in the MATLAB, that is salt and pepper. Okay, when you apply the salt and pepper noise on the image, median filter will going to remove both salt and as well as pepper. Okay, whereas the max filter will going to remove the black pixels, that is pepper noise, and salt, that is white pixels, will going to remain in the image. So min filter will going to remove the white pixels, that is salt noises, and the black pixels, that is pepper noises, will going to remain in this one. So usually we will be using median filter to remove the salt and pepper, that is both uh, black and white pixels noises in the image. Okay, so this is one such example. Unsorted array, we're going to sort it and we're going to take the median of that one, and by this median you're going to clear both the salt and as well as pepper noises in the image. So shall we see the example of this one? Yeah, this is the board. This is the board. Here, salt and pepper noise has been added on this one. And when we apply a small averaging mask of 3 cross 3, it is going to remove a little bit. But if we use the median filter of 3 cross 3 same size, we're going to get this image. Okay, when you compare all three images, which one is looking better and which one is best suitable to extract the features? Obviously the third one, the third image. It is a noise free image. We have denoised the image, so it is very clear and each pixel you can see properly. Yeah, so median filter is very helpful to remove the noise in an image of black and white color pixels noises. Okay, so I already explained to people that smoothing special filter and sharpening special filter. There are two types of enhancement filters. Okay, smoothing we have already seen now. Sharpening is just opposite to that one. Okay, so if the image is there, this is the original image. Okay, we're going to apply T of R, some transformation function, the smoothened image. Okay, this smoothened image will be the input for the sharpening special filter. Okay. Here all the pixels are smoothened, and sometimes what happened, this too much of smoothing will going to uh, you know makes us to lose some information in the image. So the smoothened image will be the input, and you're going to apply some transformation. Okay, these equations are there here. You're going to get the sharpened image. Okay, so sharpening special filters are used to highlight fine details in an image, enhance detail that has been blurred. Okay, if you see here, it has been blurred. When you smoothen the image, it has been blurred. Okay, and you cannot extract the fine particles in this one, fine information, that is minute information you cannot extract in this image. Okay, so first order derivative and second order derivative, two types of derivatives are there. Df by dx, that is delta f by delta x, is equal to f of x plus 1 minus f of x is the first derivative we have already seen in the previous classes, and the second order derivative is given by delta square f by delta x square is equal to f of x plus 1 and plus f of x minus 1 minus 2fx. Okay, the combination of both, that is smoothing special filter and sharpening special filter, is the combining special enhancement methods. Okay, so you're going to first smoothen that one, and then you're going to uh, convert that one to the gray level scales, and then you're going to enhance that one, and you're going to get the combination of these two. So combination of smoothing and sharpening, you're going to get the clear image. Okay, so in this session I have explained the background of the image enhancement in the spatial domain. The background is all about g of x comma y is equal to t of f of x comma y. The background, we have seen some basic relevant transformations we have seen, such as negative image, logarithmic transformation, then contrast stretching, etc. And histogram processing we have seen with the four images: dark image, bright image, low contrast image, and high contrast image. Enhancement using arithmetic and logic operations we have seen, that is when you use the AND mask in MATLAB, you can get those masks directly, AND mask or mask, we have seen that one. Then basics of spatial filtering we have seen. In the spatial filtering there are of two types, that is two types of filters, that is smoothing spatial filter and sharpening spatial filter. So smoothing spatial filter will be used to remove the noises in the image, and then the sharpening special filter is used to extract the minute information from the image, that is the exact opposite working procedure of the smoothing spatial filter. Combining these two will going to give us the combining spatial enhancement methods. Okay, so I have shared the notes, PowerPoint presentations, and as well as the question bank to you people. I hope this demonstration will also help you people to get some of the answers in the question bank. If you get doubts in the question bank, you can call me anytime. I'll be available for you people. Okay, so I'll be expecting the assignment in question bank to be answered by you yourself. So you can type yourself and submit the assignment on or before 14th April. Okay, so in the next session, I'll be teaching you people about image enhancement in the frequency domain. Okay, so that's the end of module 3, image enhancement in the spatial domain. Thank you.